Hi, you guys. Yesterday we learned about the parts of an atom and protons, neutrons, electrons. A little bit about the history of the atom as well, how we arrived at what we think it looks like now, or at least a good model for you. And today we're going to get into what happens when you add or subtract neutrons and electrons in an atom. What do you call that, and how do you calculate those things? So we're going to get more into the structure of the atom today. And for this one, you probably will need a calculator and a periodic table to do things correctly. And you probably should write down most of this, so feel free to pause whenever you want to make sure that you are getting all of it. Okay, because I have to do a bunch of calculations on you, I instead of doing a PowerPoint on the computer, I'm just doing it on my iPad, so I'll have to write some things down just like you. So we learned the other day, atomic numbers are the numbers of protons. They're always whole numbers. You can't just have half a proton. And most often, atoms are neutral, and so the atomic number also often equals the number of electrons in atoms. So if you had 10 protons, you would also have 10 electrons, and you would be neon. Like it says there, atoms to be neutral, the number has to be equal to protons to electrons. Every atom, let's just stick with neon, which has 10 protons, every atom of neon has exactly that number of protons. However, sometimes you don't have to have the same numbers of neutrons and electrons. And we'll start with neutrons right now. So if it's the same element that has a different number of neutrons, we call those isotopes. So it's the same element, let's just say with neon. Most atoms of neon have 10 protons, 10 neutrons, and 10 electrons. But some atoms of neon might have different numbers of neutrons. They're still neon because they still have 10 protons, but since they might have different numbers of neutrons, they're called isotopes. These are naturally occurring. So, and nerds already know them. You can look up all the isotopes for every element you want on the internet, and you can find them and read about them, and it's really exciting. But we already know exactly what percentage of each isotope is available for each atom. Okay, so one thing that becomes important then is calculating mass number. Mass number is the sum of the protons and the neutrons in the nucleus of the atom. So just keeping track of what's going on in the nucleus. You can calculate the number of neutrons by subtracting the atomic number from the mass number, if like it's written there in yellow. However, I mean, if you, like any algebra equation, if there are three variables and you know two of them, you should be able to figure out the third one. So if I gave you atomic number and mass number, you could calculate neutrons. If I gave you atomic number and neutrons, you can calculate mass number very, very easily. And an example would be just looking at like one like this, where you've got protons, electrons, and neutrons. And I want to know how many protons, neutrons, and electrons are present in an atom of copper whose atomic number is 29 and whose mass number is 64. So you have to be told this information. If you want to answer this question, you need to know the mass number. So that is given to you in this problem. Now, this other number, 29, the atomic number, you don't have to be told that, because if I told you it was copper, right, then you would say, what about your periodic table? And say, oh, copper. Well, I can find the atomic number of copper because I can just use my periodic table and look on the periodic table and say, oh, copper, the atomic number is 29. And so you're not always told what the atomic number is, because it's assumed that you have a periodic table and you can look it up without a problem. So in this problem, if you wanted to calculate the mass, it says calculate protons, neutrons, electrons. I often write them as, let's switch to white here. I often write them as like this: proton P plus because it has a positive charge, neutron N0 because it has a negative or a neutral charge, and electron E minus because it has a negative charge. And if I want to calculate all of them, I'm told in the problem that this number of protons is 29. You could look it up in the periodic table too. Doesn't say anything about the charge, so I think for right now, what is happening? For right now, you can definitely just assume that, unless you're told otherwise, the number of protons and the number of electrons is equal, so we're going to also call that 29. The trick is to find the number of neutrons, and to find the number of neutrons, what you do is you just take the mass number, which is given to you, 64, minus the atomic number, 29, and you would get 35 neutrons that would go there. So in this particular atom of copper, it has 29 protons, 35 neutrons, and 29 electrons. Do all atoms of copper have 35 neutrons? No, they don't. Those are what are called isotopes, but all of them will definitely have 29 protons. And usually they'll have 29 electrons too, but that can change sometimes as well, which we'll get into later. Okay, pretty easy. So if you're given two of the numbers between atomic number and mass number, and neutrons, you should be able to find the third one very easily using this equation right there. Okay. So because there are so many isotopes, it's useful to represent them lots of different ways. And usually that's written like this. You say the name of the element and then a dash and then the number afterward. The number is the mass number. Okay. So helium-3 is an atom of helium where the mass number is 3. Remember, mass number is protons plus neutrons. Okay. Copper-64, same thing. That's the mass number, and the mass number is protons plus neutrons. Okay. Like we just learned in the last problem, copper is always going to have 29 protons, but this number, the mass number, can change based on if you add or subtract neutrons to it. Okay. And if I'd said to any of these, like, how many protons, neutrons, electrons, and let's just say in this helium-3, how many protons, neutrons, and electrons in helium-3, well, it's assumed you have a periodic table. So you could find the protons and electrons very easily by looking at the periodic table and saying, oh, helium, that's element number 2. So it has 2 protons and it has 2 electrons. Now, if I want to find the number of neutrons, this is the mass number, remember? Mass number equals protons plus neutrons. And I already know protons, and I know a mass number, right? It's 3. So what you're essentially saying is 3 equals 2 plus x, right? So you're just going to solve for x or just subtract 2. I'm sure you can do it in your head. And so this has 1 neutron. Okay, and that's how we get the mass number 3, because 2 plus 1 equals 3. You can also represent them this way as well. It means the same thing. So this one, written as helium-4, can also be this. It means the exact same thing. Those two things give you the same amount of information. So the mass number is on top here in the symbol, and the bottom number is the atomic number, and obviously that's the element symbol there. You can calculate protons, neutrons, and electrons from either one of these and get the same number. And just like we did on the last side, right? So sometimes they don't give you the atomic number, because where can you find it? On your periodic table. So sometimes you would just have, like, this would not be there, and you would just have the helium with the 4 on top, and that means the same exact thing, and it still gives you the same information because it's assumed that you can find a periodic table and look for the atomic number of helium. So that's called isotope notation. Here, I'm going to make up a couple, and you can try them. So how many protons, neutrons, and electrons in the following? Let's call it, I don't know, chlorine. Let's say it's, I'll write it out, CH. Chlorine, I don't know, 40. Is that going to work for us? Sure it will. Okay, so to find the protons and electrons, you look on the periodic table, and you'd see, chlorine, in the upper left-hand corner of your periodic table, there's a number 17. So chlorine has, in this chlorine isotope, 17 protons, 17 electrons. Actually, all chlorine would have the same. Then, if you want to find neutrons, remember this is the mass number, so you just take 40 minus 17 to get your number of neutrons, and so that would be 23. And you can get the same information if you tried it with, like, let's say, I don't know, zinc. If this said, and I'm going to have a 30 here, and I'm going to have a 64 there. Okay, if I want to know the number of protons, neutrons, and electrons for this zinc, well, I have all the information right there. You can use a periodic table too, right? You don't need this number. You can find that in the periodic table, but that's the atomic number. The top number is the mass number. So find protons and electrons. At least for right now, we're just going to assume that they're equal. They won't be later. And then if you want to find the number of neutrons again, this is the mass number. You can almost like think of it like that, set it up like a subtraction equation like that. You're going to take 64 minus 30 and get 34. Okay, so hopefully you pause those to try them, which is a thing I forgot to mention. All right, so that's how you calculate protons, neutrons, electrons in common isotopes. But if you look in the periodic table, there's one more number, actually the number we've been using and on the bottom for molar mass. It actually has 2 meanings. Sometimes it's called average atomic mass. And what they do is because protons and neutrons weigh different amounts, and if you have more or less neutrons, you're going to have different masses for that atom. What they do is they just take an average of what the average atom weighs for each element and puts that in the periodic table. And that number is the number we use for molar mass. It's the number at the bottom of the box for each element in the middle of your periodic table. And they use a weighted average to calculate them. So if you just take a look at, like, let's say, I don't know, I'll pick one out. Here's what it looks like. And let's say it's nitrogen. And then the number on your periodic table, there's a 7 there, that's the atomic number, but the bottom number is 14.007. Okay, and each proton has what we call an AMU. That's like a number that they use to determine what the mass is. So like this would be, sometimes it's called, we use it as 14.007 grams per mole, but it's also known as 14.007 AMU. And you can convert AMUs to grams very easily. We don't really do that in this class, but it's just an easier way of saying, obviously an actual atom of nitrogen does not weigh a lot. So instead of saying it weighs like 0.0000 and then a bunch of zeros, grams, which would get very, very long. Instead, they just say it weighs like whatever, 14 AMUs, which is a shorter way, and you can convert between them, but it's not really important for this class, but if you see AMU, that's what they're talking about. Okay, so then this number, there's no actual atom that weighs 14.007. It's impossible. So what is actually going on is that they just take the average and they put that number on the periodic table. So if you had a big sample of nitrogen, the average atom would weigh that. And they use a weighted average scale, just like our grades. And in this class, our grades are 40% tests, 30% quizzes, and 30% homework. And so, if you got an A on all the tests and an F on all the homework and an A on all the quizzes, your grade is not, it's going to be closer to an A than it is to an F. That's a weighted grade average. Maybe you've calculated that before. Probably not, though, because I'm sure there's some website or some app on your phone that just does it for you. But you can learn how to calculate it now because you can do these problems and calculate the average atomic mass very easily. So here's a problem like that, where we're going to calculate the average atomic mass for this rubidium. They give you the isotope name. So this is rubidium 85. This one's rubidium 87. And they each have their own masses. This one is 84.911.794 AMU. And the other one is 86.909.187 AMU. And these go out to a lot of places because they want to be as accurate as possible. That's why the numbers are so long. But if you want to calculate the average atomic mass of rubidium, you can see that the rubidium, 72.2% of rubidium is this one, rubidium 85, okay? And 27.8% of rubidium is rubidium 87, which is this guy right there. And you would imagine then that since more comes from rubidium 85, then because the percentage is 72.2, then when you do this weighted average, it should be close to this number, okay? Because that carries more weight than the other average. So here's how you calculate a weighted average. You're probably familiar with regular average, where you just add up numbers and then divide. In a weighted average, you actually don't divide, and so that's a really common mistake. What you do is just take the percentages times the AMUs. So for rubidium 85, we've got 86.909.187. You're going to take that number times the percentage number. Make sure you convert your percentages to decimals. So rubidium 85 right here is 72.2%, so 0.722%. So you're going to do that one, and then you're going to add it to the other one. And you're going to do, let's see, so the other one is 84.911794, and that average is 0.278. Okay, you're going to add those two numbers together to get the weighted average, and if you do that correctly, the weighted average ends up being 86.3539, and then the label will be for AMUs. Now, does that number make sense? Well, yeah, it makes sense because it's pretty close to this one, right, the rubidium 85, because that's the 72.2%, but it is a little bit less than that one because rubidium 87 has a lower AMU, so it should drag that number down a little bit, and it does, but it's certainly much closer to rubidium 85 than it is to rubidium 87 because rubidium 85 has the 72.2%. Kind of like, again, if my class was 90% tests and 10% homework, and you got an A on all the tests and you got an F on all the homework, your grade would still be pretty close to an A because the 10% that you got per F's would carry a lot less weight, and that's what they're doing. Is there one rubidium that weighs that amount? No, there's not. But if you have a sample of rubidium, a giant sample of it, then the average would be very close to that. Okay, this has been a fun exercise in calculating atomic mass and also